Okay, the next thing we're going to look at are electrolytic cells, or in our electrolytic cells is electrolysis. Electrolysis means, lysis means breaking or pulling apart. So this is the electrolysis of water that we're going to look at here. And we're literally going to take water molecules and try to break them using an electrolytic cell. So in this space, let's draw in a beaker. Maybe that doesn't maybe need to be quite that big, but oh well. We've got a solid carbon electrode on both sides. So both of these are carbon solid. And we're going to draw a power source here with a negative and a positive. Maybe even run it over here just because I'm bored and lonely. It's plugged into the wall. That. Anyway, so in this beaker, we're going to put water, obviously, and then sodium hydroxide. So we're going to have Na positives. Let me actually write that a little smaller. We're in more in the middle. Na positives and OH negatives. Okay? So if we want to predict our reaction, that's what we're dealing with. And that's all that's going to be in here, because the carbon we're going to ignore. So I have Na positive, OH negative, and water. And that's it. So if we go to our data booklet, remember that water's on both sides. So it's on this side as an Ra and right over here as an, or OA over here, and an Ra up above there. Na positive is right here. It's a really weak OA, even weaker than water. And OH negative is, if I can find it here, where's the one I'm looking for? Right up, just above from where I can point to. There's 4 OH negatives right there at positive 0.40. Okay, so out of the options, water is actually my strongest oxidizing agent in this case, and the hydroxide is my strongest reducing agent. Oops, wrong one. I want to go back to this one. Let's turn off that page. So those are my two. So I'm going to write the water OA reaction backwards. So that's 2H2O plus 2 electrons becomes H2 plus 2 OH negative. And then I'm going to write that hydroxide reaction backwards. 4 OH negatives are turning into O2 plus 2 H2O. And the voltages, the water reaction we wrote forwards, so that's a negative 0.83. And the hydroxide reaction is positive on our table, but we have to flip it so it becomes a negative 0.40. Well, I didn't put my electrons on the hydroxide. 4 electrons. Plus 4 electrons. Now to balance our electrons, if we wanted to combine these, I've got 2 electrons here. So I would have to double this one so that I'm gaining 4 and losing 4. Now those will wipe each other out. So now I can combine this into 2H2O plus 4OH negative becomes H2 plus O2, sorry, 2H2 plus O2 plus 4OH negative. Now, an interesting thing happens here. We've got 4 OH negatives on both sides. So this actually goes away because it cancels out, leaving us with a net reaction of we start with water and we split it into hydrogen and oxygen. And that's it. The net voltage should be a negative 1.23 volts. That's what it would require to do this. And we should see bubbles. Now, if we were to look over here, remember that we can label on here the direction of our electrons because we know that this is the negative terminal. So no, the electrons are going this way. This is my anode and this is my cathode. And we can figure out what's going to happen at each of these electrodes. So for example, water is my OA, it's being reduced. That half reaction is the cathode half reaction, and that half reaction is producing hydrogen gas. So at this side, I'm going to get bubbles of H2. On the other one, the hydroxide is my strongest reducing agent, so it's being oxidized at the anode, and at the anode I'm producing oxygen gas. So over here I'm producing bubbles, but these are bubbles of oxygen gas. And that's the purpose of this little doohickey right here. So that on one side, as the bubbles are being produced, they get trapped in the test tube. And so you can actually collect in there samples of pure oxygen and pure hydrogen gas that you can then test and experiment with and do whatever you'd like or need to with. So that's the idea of, or the purpose of that thing there. Okay, so that's electrolysis. Nothing new about figuring out what's going on. One good thing to point out here is make sure you know how to predict the gas being produced and where it's going to be, and this is kind of what it's going to look like. Okay, now let me see if I can show you it in practice. Okay, we are back to our little lab setup over here. Here is our beaker with sodium hydroxide solution in it, and we've got a couple of carbon graphite electrodes so that those are going to be inert. They're not going to mess with anything. And we've got our power source. So we're going to hook these up. One to the positive and one to the negative. And keep those apart. And turn this on. Now I'm going to crank this up just so you can see this a little more dramatically. Maybe not quite that much. There we go. So you can see hopefully the bubbles being produced there. Let's see if I can get you a little closer. So you see the bubbles coming off of those two electrodes. Now if I turn this voltage down a little bit so it's not quite as noticeable, you should be able to notice that one of those electrodes is producing more gas than the other. And I'll show you why that is in a second. But that's basically what this would look like in operation. Put that back. All right, back over here now. So the reason is, if you look at our balanced equation, we're producing 1 oxygen and 2 hydrogen. So the way this reaction balanced, that's better. The way this reaction balanced, we're going to produce twice as much hydrogen as we are oxygen. And you can see that by looking in the half reactions. So a test question might ask something like, you're looking at this thing, maybe you don't know which side is hooked up, which one's the anode, which one's the cathode, but one is producing more bubbles than the other. If you figured out the net reaction, you could figure out exactly which one was cathode and anode because one is producing twice as many bubbles of hydrogen gas as the other is of oxygen gas. Another type of question that sometimes comes up is maybe not necessarily the hydrolysis of, electrolysis of water, but of another chemical. And in any reaction, they may say, what bubbles would you expect to be produced at the anode or the cathode? And this is how you do it right here. Look at your half reactions, and you can see right here in my strongest oxidizing agent, my reduction half reaction, I'm producing hydrogen, so that's going to be at the cathode. In this one, my oxidation half reaction, I'm producing oxygen, so that's happening at the anode. Okay? Hopefully that makes sense. If you have any trouble with any of this, let me know.